Welcome. This is the first assembly language video on instruction set architecture. Look at the class wiki for some links. Thanks, of course, to Mark Clement of Brigham Young University for most of the content on these slides. So here are some learning objectives for instruction set architecture. We want to explain what is computer architecture, describe the differences between a Harvard and a von Neumann machine, describe the differences between a RISC and a complex instruction set architecture, explain the addressing modes of the MSP 430, discuss computer instruction cycles, and be able to disassemble MSP 430 instructions. The topics are instruction set architecture, von Neumann versus Harvard, RISC versus complex instruction set, computer instructions, MSP 430 instruction set architecture, ALU and the registers, assembly primer, more MSP 430 instructions like double operand, single operand, and jumps, and addressing modes for the MSP 430, instruction length, clock cycles, and instruction disassembly. So we're really starting to get into things now. So what is the instruction set architecture? It's where the processor stores or obtains memory is part of that. Memory organization, the address space, how many addresses can be, or locations can be addressed, how many bits per location, what register set you have, how many they are, what size they are, and how they can be used, input-output devices, how the processor manipulates the data, assembly language instruction set, which includes opcodes, data types, addressing modes, processor hardware actions, flow and faults. Basically, the instruction set architecture defines all the programmer visible components and operations of the computer. And when you have all the instruction set architecture, you have all the information you need to program in machine language or to translate a high-level language to machine language. So let's look at the Harvard versus the von Neumann architecture, and first we'll look at the Harvard architecture. The Harvard architecture is a computer architecture with physically separate data storage for data and instructions. In other words, the computer will execute instructions and it will work on data. So the actual program is in the instruction memory and the data which it works on is in data memory. And this diagram here shows you a Harvard architecture. And notice it has instructions and data memory separate. Examples of the Harvard architecture are the 8051, the Atmel AVR, and the ARM. Now let's look at the von Neumann architecture. There's von Neumann over there who proposed this in 1946. Famous mathematician. So here's what he said you could do. You could have a processing unit. It has ALU, clock, control logic, a program counter, and instruction registers. Instruction register and regular registers. And you just have one memory. And one address bus going to the memory and one data bus going to this processing unit. So in this situation, you can have your program stored anywhere in memory, and your program can even modify itself. And so the idea is they're both stored in the same memory. The input addresses the memory. You can have stuff that puts things directly in memory. In memory, it also puts stuff directly out to different forms of output. as well as the processor can access those input and output as well. So then there's another way of classifying processors, and this classification has to do with the instruction set. There's the complex instruction set, CISC, and the RISC instruction set, RISC. The CISC is a little bit older than RISC, and so what are the differences between these two architectures or instruction sets? The RISC is run on a single clock. It has a reduced number of instructions. It doesn't have as many fancy instructions. There's no microcode. Data is explicitly accessed. In other words, you have to read in from the memory and write out to the memory. It's easier to validate. In other words, the RISC is simpler. It's a simpler hardware, and so it's easier to make certain that there isn't a bug in the hardware. The code sizes, in other words, how much memory your code takes up, are larger, approximately 30% larger. Generally, RISC architecture has a little bit smaller number of cycles per second, and more transistors on memory registers. It's friendly for pipelining, and the emphasis is on software. So let's look at the complex instruction set. It has multiple clocks. It has complicated instructions, complicated microcode, memory-to-memory options. It's difficult to validate, smaller code sizes, it's higher cycles per second, and more transistors for complex instructions. And it's compiler friendly. In other words, the compiler doesn't have to be quite so smart, but the emphasis on this kind of instruction set is on the hardware. So here's the IA32 complex instruction set. You can see quite a few instructions there. Here's the MSP430. It's a reduced instruction set. You can see just a few instructions there. There's the arithmetic instructions, the logical instructions, jump instructions, and the special instructions. So there's like 27 for the MSP430. So let's take a closer look at the MSP430 architecture, because we're actually going to be programming MSP430s in assembly language class. And so we need to understand kind of what's in there. This is a simplified diagram here. In general, the MSP430 has a clock. It has some flash memory. Flash memory is memory that you can program, and it will save your program even when you turn the power off. There's RAM. RAM is random access memory, and it's faster than flash generally, but you're liable to lose the contents of the RAM if you turn the power off. There's a JTAG debugger for the MSP430, an interface for that. And there's some other clocks that are used for digital peripherals, the A clock and the SM clock. And there's also some analog to digital converters and other kind of things like that. So there's actually a lot of different variations on the MSP430. There's quite a number of different MSP430 series devices to pick from, and they all have different peripherals. That's the biggest difference usually. So there's the CPU. There's the instructions and data, and here's the I/O. And there's this thing called the von Neumann bottleneck. That is that both, or everything is trying to address the same address bus, the MAB and the MDB, main data bus and main address bus. So let's look at computer instructions. What are these? So a computer program consists of a sequence of instructions that are executed in order. Instruction basically gives you a verb plus an operand. In other words, do this to this. It's stored in memory as ones and zeros, just like all other kinds of data. It's called machine code. Instructions are fetched from memory. The program counter holds the address of the next instruction or operand. The instruction is stored to the CPU in the instruction register. Programs execute sequentially through the memory, and execution order is altered by changing the program counter. So you can jump and things. A computer clock controls the speed and phases of the instruction execution. Now, what's the difference between machine code versus assembly code? What's the difference? So machine code looks like this. And if you take and you put that through what's known as a disassembler, you can see assembly code, which is more readable by humans. And here's what it is. So this assembly code over here is usually what we will be using, but you should be able to go back and forth between machine and assembly code. And I can tell you, when I took this class, we would write assembly code, but then we had to translate it into machine code and type that in bit by bit, or actually we did typed it in hex, so we were actually typing it in 8 bits at a time. There was a little keypad, a hex keypad we used to type in the machine code. It was on an 8-bit 6502 processor. At the very end of the class, they showed us this wonderful thing called an assembler, which would automatically, it was a program that would automatically take the assembly code and it would turn it into the machine code. And that was like, wow, I want one. So that's the assembler. And of course, we didn't have a disassembler either. We had to disassemble it by hand. There's also a thing called a disassembler, a program that will do that. So let's look at the anatomy of a machine instruction. The one we'll look at is add the value in register 4 to the value in register 5. So add R4, R5. So what this does is this takes the value in register 4 and adds it into register 5 and stores that in register 5. So here's the machine code for that assembly code. The verb, the add, is the first 4 bits. And the next 4 bits tell you what the first operand is, the source operand. The last 4 bits tell you what the destination operand is. So how many instructions are possible with a 4-bit opcode? Well, seems like maybe 16. How many source destination registers can be selected with a 4-bit field? 16 again. So let's look at the next thing is instruction addressing modes. Machine instructions operate, that's the verb, on operands, which are the objects. Addressing modes define how the computer identifies the operand or operands of each instruction. So you can have the mode encoded within the instruction. You can determine the size. You can determine the size of the instruction. Operands are found in registers, instructions, or memory, directly or indirectly. That means a pointer kind of like you have in C. Or you can use indexed. In other words, it will advance the thing kind of like an array. Oops. So let's go on and look at the MSP 430 instruction set architecture, and let's look at the bus architecture. So the memory bus is unidirectional. The memory address bus, that means it's going only one way. It goes from the CPU out to the RAM. The address space is the number of possible memory locations, and that's basically tells you your memory size. So there's the memory address bus, they call it the MAB. The memory data bus is actually bidirectional because the CPU can send data to memory to be written to memory, or we can read from memory to be written to the CPU. The number of bits stored in each memory location, that's the addressability. And words are always addressed at an even address. It's little endian. So there's the memory address, or memory data bus. Then there's 16 16-bit registers. So each of these registers can hold a whole word, and there's 16 of them. Remember, we looked at the machine instruction, and saw it had 4 bits to encode which register we were talking about, and that's why we have 16. Register 0 is a very special register. It's called the program counter, or PC. We talked about that before. That keeps track of what the next instruction to be executed is, where it is in memory. There's a thing called the stack pointer, which we'll get into later. It keeps track of a location in memory. Then there's the status register, which has things such as whether it overflowed or what happened. Other flags in there that tell us what might have happened when you just completed an operation. And there's the constant generator, R3, and there's a bunch of general purpose registers, 4 through 15. 16-bit arithmetic logic unit does all the arithmetic and those kind of operations. It sets the flags Z, C, N, and V. Z is a 0 flag set on when your result is 0. C is the carry flag when there's a carry. N is the a negative flag if the result was negative. And V is the overflow flag, which happens when you do have an overflow operation. Master clock, or M clock, drives the CPU and ALU logic, which is in that section right there. So let's look at the MSP 430 memory architecture. If you look at memory, basically this is a 16-bit device, so it can address up to 64,000 roughly memory locations. The top of memory, in other words the highest address numbers, are where the interrupt vectors are at 0xFF and just a bit before that. Then right under that is the flash memory. That's where we can store things that won't be destroyed when you turn the power off. And then below that is the RAM. And not all of this memory is populated in every MSP 430 variant you get. So that's something to think about. And there are actually some MSP 430 variants, including I think the one we're using, that actually allows more memory than 64K here. That it has a few extra instructions to take care of those larger memory space. And then the low memories from 0 on up to I've forgotten exactly what. I think it depends on the exact processor you've got, where the the special function registers and the peripheral I/O configuration and so on is. So we've kind of gone over this here. 64K and flash and ROM is used for both code and data, but it's stuff that you won't erase, not volatile. And then the RAM is volatile, and then the I/O is down at the bottom. You get information in and out of the computer with it, and that's, I guess, the lower 512 bytes. And so those are 16-bit peripherals in the lower 512 bytes. 8-bit peripherals are in the very lowest bytes. And special functions, I guess they're in the lowest, the very lowest, the last 16 bytes, 10 in hex. So what have you got for ports in the MSP430? Well, it communicates the external world through 8-bit memory locations called ports. Each port is independently programmable as input or output, so you can either send a digital signal out or read a digital signal in. You can have edge selectable input interrupt capability, and you can have programmable pull up or pull down resistors inside the MSP430. You can set that up. Port registers, they call them P, and then there's usually a number and an in. That's read from a port. P1 in would read from, that would be the port 1 that you could read input. P1 out, that would mean, write an output to that port. Whoops. And there's this thing called the P, and then you have the port number, and dir, that sets the data direction, whether it's input or output. 0 is usually input, 1 is usually output. Normally it defaults to input, I think. So here's a quiz for you. What is instruction set architecture? What is a memory address space? What is the memory addressability? What is a computer port? List some distinctive properties of the MSP430 instruction set architecture. I'll let you work on that.